Hello students, as many students requested me to solve some problems in oscillations chapters, today I am going to discuss some problems in oscillation chapter, and later I am going to continue the chapter waves that I started yesterday. So, now let me discuss some problems in oscillations and just listen the question clearly and see what I am explaining. So, try to understand the method. So, here no need of remembering the solution, just listen the question and see what I am doing, and try to understand the method and the concept. So, you can also do the same thing while you are practicing the problems. Now, let us start the class. So, first problem is, so this is problems in oscillations. So, let us discuss the first problem. So, a mass of 100 grams is attached to a spring of spring constant. A mass of 100 grams is attached to a spring of spring constant K is equal to 10 Newton per meter, 10 Newton per meter on a frictionless horizontal surface like this. This is the arrangement of mass. This is the arrangement. Now, this mass is displaced from its mean position by 0.5 centimeters and released. So, the mass is displaced by 0.5 centimeters from its mean position and released. So, then it is doing oscillations. Now, the question is find out maximum speed of the oscillations, that is A omega, maximum speed formula A omega, and the second question is find out speed at displacement x is equal to 0.3 centimeter, and third question is find acceleration in each case. So, now let me repeat the question once again. So, a mass of 100 grams is oscillating attached to a spring of spring constant 10 Newton per meter, and it is oscillating along the frictionless horizontal surface. If it is displaced to a distance 0.5 centimeters from its mean position, that means amplitude is given. So, A value amplitude is equal to 0.5 centimeters, then what we have to find is maximum speed of the oscillation and the speed of the particle at x equal to 0.3 centimeters and acceleration value for the first and second cases. Now, let us see how to find out. So, we know that V maximum is equals to A omega. So, first we have to find out the value of omega. So, mass is given, we know the angular frequency of spring mass system is omega is equal to root of k divided by m. As we know both k and m values, you can find omega value. So, that is root of k value is 10 divided by mass in kgs. So, it is given in grams. So, here mass in kgs will be 0.1 kg. So, just substitute the value 0.1. So, it will be root of 100. So, the value of omega will be 10 radian per second. 10 radian per second. Remember, while doing the problem, all physical quantities must be in SI units. So, now let us get the value of A omega. So, that is V maximum. So, V maximum is equal to A omega, that A value. So, it is given as 0.5 centimeters. So, 0.5 into 10 to the power of minus 2 meters into omega value 10. It will be 5 into 10 to the power of minus 2 meter per second is V maximum value. So, this is the answer for the first part of the problem. So, V maximum is 5 into 10 to the power of minus 2 meter per second. Now, let us see the second part of the problem, that is finding velocity at a displacement x is equal to 0.3 centimeters. So, let me do it here. So, V, so velocity expression in terms of displacement is V is equal to omega into root of a square minus x square. Now, substituting all the values which are given in the problem. So, V is equal to omega value, we find it as 10 radian per second. So, 10 into root of A value 0.5 centimeters So, 0.5 square minus displacement 0.3 square. So, into 10 to the power of minus 2 will come. So, that will be 10 into root of 0.25 minus so 0.25 square is 0.5 square is 0.25 minus 0.09. So, into 10 to the power of minus 2. So, let me write it clearly. So, 10 into root of 0.25 minus 0.09 into 10 to the power of minus 2, because centimeter square, if I take it out, that will be 10 to the power of minus 2 whole square, square and square root will cancel, so it will be 10 power minus 2. Now, simplifying this, we will get 10 into 0.25 minus 0.09, it will be 0.16. So, root of 0.16 into 10 to the power of minus 2, you will get 0.16 square root will be 0.4. So, it is 10 into 0.4 into 10 to the power of minus 2. The answer to this problem is, it is 10 into 0.4 is 4. So, 4 into 10 to the power of minus 2 meter per second, that is velocity at the given displacement. So, that is the second part answer. So, make a note of it clearly. Now, let us see how to find acceleration in each case for the given speeds, that is at maximum speed position and at this position 0.3 centimeters, how to find acceleration. Now, let us do the third part of the problem. So, we know acceleration is equal to minus omega square x for simple harmonic motion, and if you take the first case, it is V maximum, that is equal to A omega. That means velocity maximum at mean position only. So, for this particular case x value is 0, that implies acceleration is 0. So, at velocity maximum acceleration is 0. And similarly, if you take the other problem, that is acceleration at displacement minus 0.3 centimeters. Now, that can be found by A is equals to minus omega square x. So, we know the omega value, that is 10 radian per second, that is if I take only magnitude of acceleration, A is equal to 10 square, that is omega square is 10 square into x value is 0.3. So, that will be 10 into 0.3. So, it is 3 centimeter per second square is the required acceleration value. So, that is the solution for this problem. So, here you need not worry about length of this problem. I just consider the problem to explain each method, that means how to calculate velocity and how to calculate acceleration. So, both are included in the same problem. So, here you just try to understand how to solve the problem, method of the problem you try to understand. Now, let us see the second problem. Next problem. The second problem is a mass m is attached to a spring and it is oscillating with a time period of t is equal to 2 seconds. Remember, mass m is attached to a spring and it is doing a simple harmonic motion with a time period of 2 seconds. Now, if mass is increased by 2 kg, if mass is increased by 2 kg, its time period increases by 1 second, then what is the value of m? Okay. So, you understand the question. So, m is a mass which is attached to a spring and doing a simple harmonic motion with a time period of 2 seconds. Now, the modification done is, if mass increased by 2 kg, if 2 kg mass additionally added to the spring mass system, then what the time period increases by 1 second, then what will be the value of m? So, now let us do this problem. So, I will draw the diagram clearly for initial and final case. So, initially the spring mass system is like this. So, this is mass m. So, here time period of the system is 2 seconds. Now, the modification done in the system is additionally 2 kg mass is added to this m. So, then let us draw another diagram. So, this is m and additionally some 2 kg mass is attached to this. So, here m and this is 2 kg. So, total mass now is m plus 2 kgs, and now time period increases by 1 second, that means initially it is 2 seconds. So, increase by 1 second means you have to take initial time period plus 1 second. So, it will be 3 seconds. So, here this is the situation. So, initially this is the particular time period value and situation of the system, and now this is the final case. Now, let us compare both and obtain the value of mass. So, now we know that time period is 2 root of m divided by k for spring mass system, where k is the spring constant. So, now if I take the time period, final time period divided by initial time period, that means t dash divided by t, because here I can write t proportional to root m. Directly I can take t directly proportional to mass of the block attached to the spring. So, here I can compare time periods and masses. So, okay, if I take t dash by t, I will get root of m dash divided by m. So, m dash means this I am taking it as m dash. So, now you substitute the values, that is m dash value is m plus 2 and m initial mass is m only. So, now t dash value we have 3 seconds and t value 2 seconds. Now, squaring on both sides, you will get 3 square 9, 2 square 4, that is equal to m plus 2 divided by m. Now, cross multiply and solve it for m. So, it is 9m is equal to 4m plus 4 into 2 8. So, 9m minus 4m, it is 5m, 5m is equal to 8, then m is equals to 8 by 5 kg. So, this is the value of m which is attached to the spring initially. So, that is what the answer for this problem. Now, let us discuss another problem. Here the question is 2 blocks. So, first I will draw the diagram of the problem. So, problem number 3. So, here a spring of spring constant k. So, spring constant value 300 Newton per meter, and this small m is equal to 1 kg and this capital M is equal to 11 kg. So, it is given that there is this surface, that is there is no friction between this capital M and the horizontal surface. So, this is a frictionless surface on which the 2 blocks are placed, and now the friction coefficient between the 2 blocks is mu is equal to 0.4. Okay. Now, if the system set into oscillations, this is the given data. So, spring of spring constant k is equal to 300 Newton per meter is attached by 2 blocks of masses small m 1 kg and capital M 11 kg, and the friction coefficient between the 2 blocks is 0.4. Then for what maximum amplitude of oscillation, the 2 blocks will not slip on one another, that is the problem. So, the question is for what maximum amplitude of the simple harmonic oscillations of this system, the 2 blocks will not slip on one another. So, that is what the question. So, important method. So, listen carefully. Now, let us find out the required answer. So, first as k value is given, so let us find out the angular frequency of oscillations of this particular system. Okay. So, angular frequency of the oscillations of the system, let us find out. So, that is omega is equal to root of k divided by total mass that is oscillating at the end of the spring is. So, 1 plus 11 kg, that is 12 kg. So, let me write it as capital M plus small m first, then k value is 300 and mass 11 plus 1, that is 12 kg. Now, simplifying this, we will get 3 into 100 by 12. So, it is 3 ones 3 fours. So, root of 100 is 10 and root of 4 is 2. So, it is 5 radian per second is the angular frequency of oscillation of this particular system. Now, the question is about for what maximum amplitude of the oscillations of the system the blocks will not slip on one another. So, for that so the friction force between the two blocks, that is maximum friction force, that is the limiting friction, Fs maximum, that Fx maximum is equal to mu into small m into g. This force must be, that is maximum restoring force acting on small m must be equal to limiting friction force between the two blocks. Then only the blocks will oscillate without slipping. So, that is the condition. So, mu mg is limiting friction and this limiting friction force must be equal to the maximum restoring force acting on block m is equal to 1 kg. So, then only it will not slip on the other block. So, that is the condition. So, mu mg must be equal to maximum restoring force. So, what is restoring force equation? That restoring force is minus m omega square x generally, but here x I have to replace x with the amplitude. That means, if I want to find out what maximum amplitude the blocks can oscillate without slipping, so I have to replace this x with the a. So, let me write it as mu mg equal to m omega square a. So, because I know omega square value and mu and g value, here I can cancel small m. So, I can find out the value of amplitude for which the blocks will not slip on one another. So, let us find out. So, a is equal to mu into g divided by omega square. So, now let us substitute the value of mu. So, mu is 0.4 into g value 10, let us take g value 10 for simplicity. So, mu into g divided by omega value, we obtain it as 5. So, 5 square, that is 10 into 0.44 divided by 25, that is equal to 0.16 meters, or you can say it is 16 centimeters. So, that is the answer for this problem. Now, let us discuss one more problem. So, problem number 4. Now, the question is, first let me write the data for the problem, that is the time period of oscillation of is 4 seconds and amplitude is 4 centimeters. Okay. So, a block is oscillating with a time period, a spring mass system is oscillating with a time period t is equal to 4 seconds and amplitude 4 centimeters. Now, the question is, calculate the time taken by the mass for reaching from positive extreme position. So, you have to calculate time value for moving of block from positive extreme position, remember positive extreme position to displacement to a displacement equal to half of amplitude. So, this is the problem. So, particle is doing SHM with time period t is equal to 4 seconds, amplitude a equal to 4 centimeters. Now, the time taken by the particle in moving from positive extreme position to a displacement equal to half of its amplitude. So, here the question is very clear. Now, let us take the simple harmonic motion, because the let us assume that particle is starting from extreme position, so that I can use the SHM equation as y is equal to a cos omega t, because initial phase is 90 degrees. So, actually you can take this one. So, y is equal to a sin of omega t plus phi, because this initial phase is 0 when I consider the particle is starting from mean position. For example, if I take a simple pendulum, so if I assume the particle started oscillating from mean position, I can take initial phase 0. So then the equation becomes a sin omega t. But if particle is so if you assume the particle is started oscillating from extreme position, I have to take the initial phase as 90 degrees. So here if I take sin omega t plus 90, sin 90 plus omega t, it will be sin 90 plus theta cos theta. So I can write the equation as y is equal to a cos omega t. So that is what I am taking. So y is equal to a cos omega t. Now, so given condition is y is equal to a by 2. So displacement is equal to half of amplitude. Now substitute the given value in the equation. So a by 2 is equal to a into cos of omega, nothing but 2 pi by time period into t, because capital T value is given. So I am writing omega in terms of capital T. Now this a get cancelled. So here 1 by 2 is equal to cos of 2 pi by capital T into small t. So here cos function is there and this side 1 by 2 is there. So for which for the value 60 degrees, cos value is 1 by 2. So I can write this as cos of 60 degrees, nothing but pi by 3 radians. So cos pi by 3 is equal to cos of 2 pi by capital T into small t. Now taking cos inverse on both sides, you can get so let me write here. So that is pi by 3 is equal to 2 pi by capital T into small t. Now getting the value of small t, so pi get cancelled, then t is equal to small capital T divided by 2 into 3, 6. So capital T value is given in the problem, that is 4 seconds. So 4 divided by 6, so it will be 2 by 3 seconds. Okay, that is the answer for this problem. Okay, so just apply the given condition by taking the standard equation of SHM, so we will get the answer. Now let us discuss one more problem. The next question is question number 5. So the maximum speed of a particle doing SHM is V maximum. Maximum speed of particle doing SHM is V maximum. Then find out the average speed of a particle doing SHM in one complete oscillation. The question is finding of average speed for one complete oscillation of SHM. So it is a direct question, where we have to find out average speed. So let us see how to find out average speed for one oscillation of the particle doing SHM. So first V maximum is given. So we know V maximum value is A omega. So just write the formula for V maximum. That means we have to express the answer in terms of V maximum. So that is what the question means. So here, so if I take one oscillation, let us take a particle is performing SHM along the horizontal direction. This is the mean position. Say this is the extreme position and this side another left side extreme position. So I can write minus A. So now if I take the particle that is starting from mean position, if I count one oscillation, let us see how much distance it is covering, because average speed definition is average speed is equal to total distance by total time taken. So total distance, say capital small d divided by total time taken t. So first let us find out total distance. So if it starts from here, it will go this side, so it is covering a distance A, and again coming back to O, it will cover. So first A, and then again coming back to O, it will cover another A, and again moving to left side extreme, it will cover another A, so plus A. Next again moving back to O, it will cover another A. So it is, this is the total distance covered in one oscillation. So oscillation is nothing but starting from mean position and means coming back to the mean position. So, O to A to O and O to minus A to O is one oscillation. So, in that particular motion it is covering a total distance of 4A, then 4A is total distance, and we know the time taken for one oscillation is known as the time period. So, total distance is 4A and the total time taken is equal to time period of oscillation. Now, time period is nothing but 2 pi by omega. Substituting the value, you can get 4A divided by T value 2 pi by omega. So, simplifying this, you will get 2 into A. So, this omega will go to numerator, 2A omega divided by pi. So, where A omega is V maximum. Therefore, the average speed of one oscillation for the particle is 2 into V maximum divided by pi. This is average speed for one complete oscillation of particle. That is it. That is the answer for this problem. Now, let us move on to the next problem. Question number 6. The question is, at what displacement of the particle doing SHM from its mean position, the speed of the particle becomes half of its maximum speed. Means you have to find out find x value. I am taking horizontal oscillations. Find x value for which speed of the particle becomes half of its maximum speed. That means V maximum divided by 2. This is the question in brief. So, the question is, a particle is doing SHM along horizontal direction. Find out the displacement value at which the speed of the particle becomes half of its maximum speed value. That is the question clearly. So, that I represented in brief form. So, V equal to V maximum by 2 is the condition. So, this is the condition. Now, let us take the formula for velocity of a particle in terms of displacement. That is V is equal to omega into root of A square minus x square is the V value in terms of displacement. Now, let us use the given condition. So, V maximum, we know that V maximum is A omega. Now, let us use the value of A omega here. So, that means V is equal to V maximum A omega divided by 2, that is equal to omega into root of A square minus x square. So, I just substituted the given condition in the formula A omega by 2. Then if you solve it for x, you will get the required answer. So, now let us solve it for x. Omega get cancelled. Now, squaring on both sides, this side will get A square by 4 and that side will get A square minus x square. Now, x square is equal to, so x square becomes plus, so plus x square is equal to A square minus A square by 4. Now, simplifying this, you will get 4A square minus A square, that is 3A square by 4 is equal to x square. Therefore, x is equal to 3 root 3 A divided by 2. That is the answer for this problem. Now, let us see the next problem, that is question number 7. So, for what value of a displacement the kinetic energy of a particle is equal to potential energy? This is the question. At what displacement from mean position from mean position, kinetic energy of particle is equal to potential energy of the particle. This is the question. Now, let us take the expression for kinetic energy and potential energy, and let us see at what displacement they are equal. So, here we know kinetic energy in terms of displacement is given by k is equal to half m omega square into a square minus x square is kinetic energy expression, and potential energy half m omega square x square. Now, if you equate these two and solve it for x, you will get the required answer. Now, let us solve it. So, half m omega square into a square minus x square, that equal to half m omega square into x square. So, half m omega square get cancelled. So, this side a square minus x square, that equal to x square. So, it implies 2x square is equal to 2x square is equal to a square. So, x square is equal to a square by 2. So, x is equals to plus or minus a divided by root 2. So, this is the required answer. So, at displacements x is equals to plus a by root 2 or minus a by root 2, the value of kinetic energy and potential energy are equal. That is the answer for this problem. Now, let us see another problem that is question number 8. The question is, so first let me draw the diagram related to the question. Two identical springs this is the system given. The two springs are identical, that means their spring constant is same, and let they are attached to a rod of mass say 2m and the length L. Mass 2m, so uniform rod of mass 2m and length L, which is connected to the two springs as shown in this figure. Now, the rod is free to rotate about its midpoint in the plane of the ball. Just imagine, in the plane of the ball it is free to rotate. Now, the question is, what is the time period of oscillations of the rod? What is the time period of oscillations of this particular rod? So, in this case, so the two springs will, so here the, if you just displace the rod by a small angular displacement, means if you just give a small angular displacement about the center of the rod, the system will oscillate, because here the springs are attached at the end. So, they will provide the couple for the rod, so that it will do oscillations, angular oscillations about the midpoint, about the center of the rod. So, now let us calculate the time period of these oscillations. So, let me explain the diagram first. Let us draw the diagram. So, this is the spring. Let the rod is displaced through a small angular displacement. This is the midpoint of the rod, and this is the other end. So, like this. So, let this angular displacement is theta. So, this can be the compression of the spring. This is, so this much the spring will be compressed when I tilt the rod through an angle theta. This much compression will happen in each spring, because they are identical springs. So, this also I can write it as x. Now, for calculating the restoring torque acting on the rod, we need to find out the perpendicular distance. So, as this angle is theta, so this angle I can take it as theta. And now, now let us find out the restoring torque. So, we know very well that when a system is doing simple harmonic oscillations, there must be a restoring force or restoring torque. In this case, the two spring forces, say Kx and this force is also Kx. They are equal and opposite forces acting at the ends of the rod, so that the rod will experience some couple that will act like a restoring couple, like oscillations of a dipole in electric field or oscillations of a magnet in a magnetic field. So, same kind of situation. Now, let us find out that restoring torque and let us apply the definition of SHM. So, you can find out the time period of oscillation. So, first let us find out the restoring torque. So, restoring torque is equal to, so here couple torque is equal to force into perpendicular distance. So, remember magnitude of any one force you have to take while calculating the couple value. So, here magnitude of any one force Kx, that is spring force is Kx, we know that. So, Kx into perpendicular distance, let us say this is the perpendicular distance AB. So, perpendicular distance AB. Now, minus K into x, the AB can be obtained by taking this triangle, because this hypotenuse can be the length of the rod. So, if I take cos theta is equal to adjacent by hypotenuse. So, let me write here cos theta is equal to adjacent side AB, which is required perpendicular distance divided by length of the rod. So, AB is equal to L cos theta. L cos theta. So, substitute here. So, perpendicular distance AB is equal to L cos theta. Now, let us find out x value from this triangle. So, because this from here to here the hypotenuse. So, if I take this small triangle, for this triangle the hypotenuse will be L by 2, that is half of the length of the rod. So, L by 2. Now, taking sin theta, I can find out x value, that is compression of each spring. Sin theta is equal to opposite side by hypotenuse side for the triangle is L by 2. So, x is equals to L by 2 into sin theta, that is the value. So, because the angle is very small, so I can take small angle approximation for simple harmonic oscillations here. So, here x value can be L by 2 into theta, because sin theta is theta for small angle. Similarly, now let us substitute the value here that is restoring torque. So, torque is I alpha, that is Newton's second law in rotational motion, I into alpha, moment of inertia of the rod into angular acceleration, that equal to minus k into x value L by 2 theta into L cos theta is approximately equal to 1 for small angle. So, L into 1 it will be L. So, L into L. Now, simplify this, minus k L square divided by 2 into theta. So, minus k L square into theta divided by 2. So, here this side is I alpha. Now, moment of inertia of the rod about its midpoint, the axis about the axis passing through its midpoint, we know that formula m L square by 12. Here mass is 2m, be careful. So, I will write I is equal to 2m into L square divided by 12, because mass is 2m. So, if it is m, so you will get ml square by 12 directly, but here mass is mentioned as 2m in the problem. So, 2m L square by 12, which will be m L square by 6. Now, use the value here, you will get m L square by 6 is moment of inertia into alpha is equal to minus k L square by 2 into theta. So, here L square get cancelled. So, 2 1s 2 3s, then alpha is equal to minus 3k divided by m, 3k divided by m into theta. Now, just compare this equation of angular acceleration of oscillations with the standard equation of SHM that we already studied, that is alpha is equal to minus omega square theta. Now, omega square value will be 3k by m. Omega square is equal to 3k divided by m. This implies omega is equal to root of 3k divided by m. Therefore, time period is equal to 2 pi into root of m divided by 3k. So, that is the time period of oscillation of this particular rod. So, that is it. So, now let us see one more problem. So, make a note of it clearly, and so you do not worry about the length of the problem, just observe how the problem is being solved. So, try to understand the method. So, just we find the value of the restoring torque that is produced by two equal and opposite forces at the end of the rod, and we calculated restoring torque. So, force into perpendicular distance, and force value is K into X, where X is the compression of the spring. That compression of the spring we obtained from this triangle. So, this angle is angular displacement of the rod from the with respect to the vertical position. So, this X value I find by using sin theta. So, after getting the value of X and perpendicular distance, we took the small angle approximation, because for large angles the oscillations may not be simple harmonic. So, we have to take that small angle approximation. So, sin theta equal to theta and cos theta equal to approximately 1. So, after getting that, so here moment of inertia. So, torque is equal to I into alpha, and that equal to minus k L square theta by 2. So, substituting the value of I, we got the value of alpha, and as usually omega value and then time period value. So, that is the method. So, try to understand the method. Now, let us move on to another problem. Question number 9. This question is about the spring. So, the question is a spring of length L and a spring constant K. A spring of spring constant K and length L is cut into n equal parts. It is cut into n equal parts. Then find the spring constant of each part that are obtained. Okay. So, here the spring of length L is divided into n parts. So, length of each part will be total length divided by number of parts. Total length divided by number of parts. So, if let K dash is the spring constant of each part that obtained after cutting the spring. Now, let us find out the K dash value. So, we know that the stiffness constant or spring constant inversely proportional to each other, means if we cut the spring, if you cut the spring into two parts, the spring constant will become double. That means spring constant and length are always inversely proportional to each other. So, K inversely proportional to L, and we know K into L is equal to constant. So, I can make use of this particular idea here. So, for both the original spring and the spring which is obtained after cutting, I can use this equation. So, I can write K into L must be equal to K dash into L dash, which must be equal to constant. Now, taking this relation, K dash can be obtained as K into L divided by L dash, because we know L dash value, that is L by N, that is K into L divided by L dash value, L divided by N. So, here L cancel, you will get N into K. So, spring constant becomes N times the spring constant of the actual spring. That is what I told, spring constant and length inversely proportional to each other. So, this is one important method. So, be clear about this. Now, let us discuss one more problem based on the same topic. Question number 10. A spring of spring constant K, let us see the spring of spring constant K and length L. This spring is cut such that this spring is cut into two parts such that one part the length of one part is twice the length of the other. So, this is cut into two parts. This is the first part of length L1, and this is the second part of the spring of length L2. So, it is divided into two parts such that the length of one part is equal to 2 times the length of the other. That is, I can take the condition, say L1, the length of the first part, that is equal to 2 times length of the second part. Now, find out the spring constant of each part that are obtained. So, that is the question. So, this is the given condition L1 equal to 2L2. So, by using this condition we have to find out the spring constants of first part and the second part which are obtained after cutting the spring. So, now let us find out K1, K2 values using the similar idea that we discussed in the previous problem. Now, we know that K inversely proportional to L. So, KL is equal to constant. So, that I can use the same relation for each part of the spring. So, KL must be equal to K1 L1, that is equal to K2 L2 is equal to constant, of course, it is constant. Now, the total length L must be equal to L1 plus L2, L1 plus L2 must be equal to L. Now, L1 is given as 2L2 in the problem. So, length of first part equal to twice the length of the second part. So, I can use that condition here. So, 2L2 plus L2 is equal to L. Now, 3L2 is equal to L, that implies L2 is equal to L by 3. Now, by using this in this equation, so for here L2 value we obtained. So, take this equation KL is equals to K2 L2. So, I can get a K2 value. So, that is K into L is equal to K2 into L2 value is L by 3. So, here L get cancelled, therefore, K2, that is a spring constant of the second part of the spring, is equal to 3K. This is one value. Now, let us find out the spring constant of the first part of the spring. Now, take this equation, because we know L2 value, you can find out L1 value. So, L1 is equal to 2L2. So, L1 value is L by 3. So, L2 value is L by 3. So, L1 value equal to 2L2, that is 2 into L by 3. Now, use this equation that is K into L is equal to K1 L1. L1 value is 2L by 3. So, here L cancel, therefore, K1 is equal to 3 into K by 2. So, 3K by 2. This is the spring constant of the second part of the spring. So, in this way you can solve any problem when they mentioned the spring is cut into the given number of parts. Sometimes they may compare the time period of obtained parts with the actual spring also. That is also another important method. So, just keep it in mind and be clear about the method. So, that is the question number 10 and its solution. Now, let us discuss one more problem. So, before discussing this problem, let me mention the concept related to this problem, that is that calculation of time period when point of suspension is accelerating. So, that is the concept. So, first let me write the formula. So, here if pendulum is this is the pendulum which is oscillating with a time period t, this is actual time period. Now, if point of suspension is accelerating, so the effective time period value, how to calculate, I already explained this in the concept video. So, that a time period can be t dash, that is equal to 2 point root of L divided by A net. So, net acceleration you have to find, because in this case point of suspension is at rest and it is oscillating. So, it will be 2 pi into root of L by G. If the point of suspension is accelerating, it may be any direction, either vertically upward direction or horizontal direction, or making an angle beta, whatever it may be. So, you have to find out net acceleration, and then you have to substitute net value in this equation, and then you have to compare t dash and t. If you take the ratio of t dash and t, you will get the value t dash in terms of t. That is the method. Now, let us do one problem based on this method. So, the first problem related to this is, so question number is 11. A pendulum is set up in a car. Question is, a pendulum is set up in a car and that car is moving in a circular path of radius r. So, radius of radius of circular path is r, in a circular path of radius r with uniform speed. So, let me explain the question clearly. A pendulum is set up in a car which is moving in a circular path of radius r with a constant speed v. Then what will be the time period of that pendulum when it is moving in the circular path? So, given m is mass of the bob. So, here given data, another given data is small m, mass of the spherical bob, mass of the spherical bob of the pendulum. This is the given data. So, the car is moving in the circular path like this. This is the car, and in this the pendulum is set up like this. We draw some big diagram, and the pendulum is set up like this. So, because the car is moving in circular path with a constant speed v, it will experience centripetal acceleration. So, the pendulum which is set up inside the car will experience same amount of acceleration which is away from the center of circular path. So, if I draw the free body diagram of the pendulum, this is actual. If there is no more, if the car is not moving, the pendulum will be doing oscillation with actual time period, that is 2 root of L by G. Because the car is moving, so it will experience a centripetal acceleration. We know centripetal acceleration is v square by r. The same acceleration will be experienced by the pendulum, the direction away from the circular path. So, this will be the situation. This is G and this is G, and this is the acceleration due to the motion of the car in the circular path with constant speed, that will be v square by r. Now, the net acceleration experienced by the pendulum can be calculated as A net is equal to root of, because angle between the two accelerations is 90 degrees. So, I can write it as root of g square plus that value A square, that is A value v square by r. So, v square whole square is v power 4 by r square. This is net acceleration. Therefore, so after getting the net acceleration, substitute back in the value of time period. So, that is t dash is equal to 2 pi into root of L divided by, remember here square root is there inside. So, it can be g square plus v power 4 by r square to the power of 1 by 2. So, this is the answer for this problem. So, remember you have to find along which direction the point of suspension is accelerating, and then be clear about the angle between G and the A value, and then use the parallelogram law of vector addition for finding net acceleration value and substitute effective acceleration in the denominator of time period formula. You will get the answer. That is one important method.